Today we're looking at Rosen, Discrete Mathematics and its Applications, Chapter 2.1, Question 47. What we were given is a definition of a set A, and index I, A sub I, is equal to the set that contains the elements 1, 2, 3, all the way up to whatever I might be. And I was going to range over all of the positive integers without 0. So I equals 1, 2, 3, and so on. Once we have a sense of what those sets are, we're going to take the intersection and the union of them from I equals 1 to n in both cases. So a good place to start is to look at what some of these sets look like, given the definition. So A sub 1 is the set that just contains the element 1. A sub 2 will be the set that contains the element 1 and 2. A sub 3 will be the set that contains the element 1, 2, and 3. A sub 4, if you guessed it, 1, 2, 3, and 4. So you can see the subscript tells us where to terminate the set. In other words, whatever the subscript is, we start with 1 and we stop at that subscript. So in the case of A sub 2, we start at 1 and we go all the way to 2. A sub 3, we start at 1 and go all the way to 3. A sub 4, we start at 1 and go all the way to 4. So A sub n then will start at 1 and proceed all the way up to the element n. So A sub n is a set that contains the elements 1, 2, 3, all the way to n. You can see all of these are finite. None of these are infinite. And so now let's look at what the union of such sets would look like. So we have the union of I equals 1 to n of A sub I, which is convenient notation. It's saying take the union of set starting with I equals 1 of A sub I, A sub 2, all the way to A sub n. A good way to think about this is if we had A sub n was actually, say, A sub 3, then our union would be A sub 1 union A sub 2 union A sub 3, and we would take the union of all of those sets. So wherever it stops, this case in my example 3, but it wants us to stop at n. So in other words, abstractly, we're going to stop at whatever element n we choose. So that's what the union means of this family of A sub i's. Now we have these sort of 4 written out here, so I can write them all the way up to A sub n, which is a set that contains all the elements up to some n. All right, so what is the union of all of these sets? Well, first is what is a union? A union will be defined as the set. Let's say if I do this a little more abstractly, if I have sets u and v, if I say there's an element x in u union v, capitalize these, this means that this is a set that has the element x such that x is in u or x is in v. So a requirement for an element in the set is that it has to be in one of the two sets. The same is true for sets from A sub 1 to A sub n. The only requirement to be in the union of these sets is that it's in at least one of these sets. And we don't repeat. So in other words, we don't count 1 every single time we see it. So we see here's a 1, here's a 1, here's a 1. Every set has 1 in it, so that's all we'll keep. This has a 2, but all of them have a 2. This has a 3. And we're going to see that this is actually the largest of these a sub 1s, 2s, 3s, all the way to a sub n's. The union of these is the largest set. So this is a sub n. So in other words, the union of a sub i's from 1 to n is actually a sub n. Again, the largest. All right. So now we want the intersection of a sub I, which again is, if we look at an example to some value, say 3, we're taking a sub 1 and intersecting with a sub 2 and intersecting with a sub 3. So we just go up until we hit our upper index point. So a sub n will take us all the way to whatever value of n. And what is the definition of an intersection? So let's use x and y this time. If I have an element x in x and y, this will be defined as all such x's, where x is in x and x is in y. So to be an element of an intersection means that that element has to be in both sets. Or in the case of our I equals 1 to n, it has to be in every single possible set. So in other words, if we look at this, and let's write out from our list above, a sub 1 is 1, intersect with 1, 2, intersect with 1, 2, 3, intersect with 1, 2, 3, 4, intersect all the way to 1, 2, 3, dot, 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 n. So we need this to have every element needs to be in each of these sets. So in other words, if I want to include 2, well, here's a 2, 2, 2, but there's no 2 in this first set. So we exclude 2 from our intersection. There's a 3 here, a 3 here, a 3 here, but there's no 3 in here, no 3 in here, so we have to exclude 3. And you can see from this list, the first set only has 1 in it. So we're going to have to exclude everything greater than 1. So the intersection of this set is actually just a set that has 1, which again is just a sub 1. So the intersection is just a sub 1. So let's write that down to recap. So in the first instance, the union from I1 to n of a sub I is equal to a sub n, and the intersection of I equals 1 to n of a sub I is a sub 1. With finite sets that are ordered in this way, you're going to find that this generally means that the union will always be the largest of the sets, and the intersection will generally be the smallest of the sets, again, when they're ordered in this particular way. So that's what these two are, and that's it. So like, subscribe, do all that stuff. Appreciate it. Thanks for watching.